So imagine you have a rectangle, but there's a catch. You don't know where the rectangle is. Instead, all you get are points from someone who does know where the rectangle is. And of course, whether or not those points are in the rectangle or not. For the sake of this example, we'll assume that all the points come from some fixed distribution D. Can you determine where the rectangle is? Perhaps, but not with absolute certainty. For instance, it could be here, or here, or here. What we can do, and what we've been doing, is generating a hypothesis. An educated guess of where we think the rectangle is based on the points we received. With these points here, all of the rectangles we previously saw were all equally as good hypotheses. For consistency's sake, let's use one way to generate our hypotheses. For this example, let's do it in the following way. For every point drawn that we know to be inside the rectangle, take the largest and the smallest x and y value. We will use these as the largest rectangle that we know exists. Now the question is, how many points do you need before you can get a hypothesis that is exactly where the rectangle is? Take a moment to think about it. Well, it might be obvious, but the answer is that you need all of the points. And well, that's not useful. Why do we need to figure out where the rectangle is if we already know where the rectangle is? So instead of figuring out exactly where the rectangle is, which would take all the points in the rectangle, how about we do something slightly simpler and a lot more useful? We get close enough with some epsilon greater than 0. How many samples do we need then? Well, for this problem, it's fairly simple to work it out. Let R be our ground truth rectangle, or where the rectangle is in reality, and let R prime be where we think the rectangle is. We can obtain a total error epsilon if on each side we have error epsilon over 4. Of course, this is being generous as there is an interval on each side which will be counted twice. Now let T be exactly this region. Naturally, the probability of a positive sample following inside this slice on each side is epsilon over 4. From the earlier statement, it is easy to follow that the probability of a sample not landing inside T is exactly 1 minus epsilon over 4. For m samples, this becomes 1 minus epsilon over 4 quantity to the m, and by the union bound, the probability of not landing in any of these regions is 4 quantity 1 minus epsilon over 4 to the m. And we want this probability to be less than some arbitrary confidence parameter delta. This problem is just one example of what one might consider a learning problem. Being mathematicians, let's abstractify a little so we can define this problem in general. Let X be the set called the instance space. This is where our learner learns, i.e. the data he can see. For example, the previous problem, this instance space X was R squared, but it can be much more complicated than that. For example, we could have a person, and this person could have a height, a width, an eye color, hair color, etc., and this could be a possible instance space. Moving on, a concept C over X is some subset of the instance space we are interested in. In the last example, it was the class of axis-aligned rectangles. And for the people example, a concept we could be interested in is, for, let's say, the class of all people who are snowboarders. Going on, a concept class is a collection of concepts. For example, in the rectangles, this would be the collection of all axis-aligned rectangles, and while it makes a little less sense in the human example, it would be just all types of people. Lastly, we mentioned in the previous example that all the samples were taken from some fixed distribution. Now let's just call this distribution D. The problem can now be formulated in the following way. We have some learning algorithm L who exists inside some instance space X. Now inside this instance space X, we have some concept that we're interested in, C. Now, after feeding L a bunch of samples, L will output a hypothesis class H. The natural measure of error for L then becomes how much the hypothesis differs from this class, i.e. the error of H is equal to the probability for all X inside D that the concept of x is not equal to the hypothesis of x. This can be shown as a shaded region in the diagram below. Now, as we saw with our dummy example, we usually need infinite samples to get the answer exactly right. This is not very computationally efficient, however, so instead, like we did before, we get a hypothesis which is just close enough. We formalize this using the PAC learning model. This stands for probably, approximately, correct. We define PAC learning in the following way. Let C be a concept class over X. We say that C is PAC learnable if there exists an algorithm L with the following property. For all epsilon delta between 0 and 1/2, with access to some way of getting samples and inputs epsilon and delta, then it is possible to output a hypothesis H in big H such that the error of H is less than epsilon. What's more, we say that C is efficiently PAC learnable if L can learn C in polynomial time in 1 over epsilon and 1 over delta. Looking back at the formula we derived in our previous example, rearranging the terms, we get that the number of samples needed is some polynomial in 1 over epsilon and 1 over delta, so rectangles in R2 are efficiently PAC learnable. Now let's see if we can do this in general. First, let's look at the case where we have finite hypothesis spaces. To do this, we need a few more definitions. We say that the samples we give our learner L is our training set. We call a learner consistent if it perfectly fits the training set whenever possible. For example, on the rectangle problem, our learner was consistent. The way we outputted hypotheses ensured that no matter how we expanded the rectangle, we always had the previous points still inside that rectangle. Next, we define the version space over a hypothesis and our distribution to be the set of hypotheses which correctly classifies these samples. For the hypothesis class capital H, we consider the version space to be epsilon exhausted if for all hypotheses lowercase h in uppercase h, the error is less than epsilon. Now consider we have hypotheses h1, h2, h3, to hk. We fail to exhaust the version space if and only if at least one of these k hypotheses is consistent with all m independent random training examples. The probability that one has error greater than epsilon is 1 minus epsilon. For m samples and k hypotheses, we get that the probability is at most k 1 minus epsilon to the m. Since k is less than the size of our hypothesis space, and 1 minus epsilon is less than e to the negative epsilon, we get that k 1 minus epsilon quantity to the m is less than or equal to the size of h e to the negative epsilon m. Rearranging, this is m is greater than 1 over epsilon quantity natural log of the size of the hypothesis space plus natural log of 1 over delta. As we can see, this is polynomial in 1 over epsilon and 1 over delta, so finite hypothesis spaces are PAC learnable by consistent learners. Alright, so what about infinite spaces? Well, let's just use the same equation. Everything works, right? Well, not really. If h goes to infinity, then we need infinite samples by the previous inequality. That's not good. Let's instead consider a different measure of sample complexity. To do this, we need even more definitions, so bear with me here. We say that H shatters a set of samples S if for all dichotomies of S there exists a hypothesis in H which is consistent with the dichotomy. Now I know what you're thinking. What? But hold on to the definition for now, and I'll give a more concrete example later where it'll all start to make a little more sense. Now, we can use this notion of shattering to introduce a new measure of complexity, which we can denote the VC dimension, or the Vapnik-Travanikis dimension. This is simply the largest set which can be shattered by H. Let's see now what this means. Let's take a look at a classic learning algorithm which you may or may not be familiar with, the single-layer perceptron. For our purposes, we can say that the output is 1 if the sign of w1 times x plus w2 y plus b is positive, and 0 if the sign is negative. This can be visualized on a graph by just a line, and a direction which classifies all sides on that direction as 1 and the other ones as 0. Now let's see what the VC dimension of this single layer perceptron is. To recall, the VC dimension is a larger set which can be shattered by h. What that means exactly is that for any number of points, for all arrangements of labels for those points, the learner can get them correct. Let's take the example with only 2 points. There are 3 possible arrangements of the labels, and here I show the lines which accurately classify those points. Therefore, we can determine that the VC dimension of the single layer perceptron is at least 2. So now let's look at 3 points. There are 4 such arrangements of labels for 3 points. Again, we can easily draw the lines which results in the correct classification of these points. Thus, the VC dimension is at least 3. Going on to 4, however, we can show that there is a labeling of these points such that the perceptron cannot get the points correctly labeled. Therefore, we know that the VC dimension of the single layer perceptron is exactly 3. Well, how is this important? Well, in a paper by Bloomer et al. In 1989, showed a bound for the sample complexity using this VC dimension, thus showing that certain infinite hypothesis spaces are also efficiently PAC learnable. Alright, so that's it for the main things we covered this quarter. We went over a few other things, but we don't have the time to go through those in detail. So yeah, thanks for watching, and let me know if you have any questions.